Mr. Isberg here, and we are looking at lesson 4.2. We're going to cover parts A and B in this video. And what those cover are, they cover the first 3 points on your notes. It looks at distinguishing between observational studies and experiments. It looks at describing the language of experiments and the 3 principles of experimental design. And we're going to try and connect these as much as possible forward. So this video should go through slide 12 on your notes packet. So let's start, and we do know a couple things, and I found this, it's on Khan Academy, and it goes through pretty well in things that you already know. The first part of 4 dealt with the sample study. We want to identify the average daily time spent on a computer by somebody. And so we have a population, which you can see in red here, and what happens is we don't have the ability to ask every single person in a large city. There could be hundreds and hundreds of thousands of people. We don't have that time. So what we do is we collect a sample, and we do it really, really well. And by collecting that sample from the population, we can then look at that sample to figure out what's going on for it. And so that's a sample study. That was 4.1. An observational study was what we did in a way in chapter 3. We looked at how a response variable relates to explanatory variable. And so let's do the same idea. Let's say I have 1,000 people and I collect data on them. And I plot how much time they spend on computer, and I apologize for the blurriness, and how much time, like what was their blood pressure. So how much time spent on the computer, hours on a computer, and blood pressure. And we look at this, what we were able to do here is we were able to describe, notice, hey, you know what, there's a relationship between these. The more time somebody spends on the computer, the higher the blood pressure they have. And so that's what chapter 3 looked at. It looked at the relationship, the correlation between 2 variables. But there's an issue with that. We learned that correlation does not imply causation. Just because there's a relationship doesn't mean that there's something cause and effect there. One doesn't cause the other. And you have to realize there could be confounding variables. I mean, you could have, in this case, a lack of activity. Somebody could just not be an active person. And if they're not active, maybe they're spending more time in front of the computer. And if they're not active, maybe their blood pressure's high. So there could be a confounding variable there, something behind the scenes causing a problem with our information. It could be impacting some of these results that we saw. There could not be a relationship with blood pressure and computer time because it could just be activity of those. So that's a confounding variable. And so that's why we can't do correlation implying causation, a cause and effect relationship with observational studies, is we're not controlling for those confounding variables. That's where 4.2 comes in. If we do an experiment, a well-designed experiment following the 3 principles of design, we can control for those confounding variables. And what an experiment does, it imposes a treatment on a group of people. And so in this case, we have, this says, can see a max of 30 minutes on the computer. And this does 2 hours on a computer. And we're randomly assigning 100 people into each group. And we're going to do it the same way random we did in 4.1. And that is the treatment. Hey, you can spend 2 hours, you can spend 30, and we're going to compare the results of the blood pressure from them. So now, by that random assignment, we're controlling for that confounding variable. That's kind of what we did. You know, this was chapter 3, this was 4.1, and this is 4.2. This is what we're looking at today for it. So I've already kind of talked about observational studies versus experiments. I just kind of want to show you a visual of it. So what an observational study does is it observes individuals and it measures variables of interest, but does not attempt to influence. There is no influence. You're just observing what's going on. It examines the relationships between variables. But what an experiment does, an experiment deliberately imposes a treatment on individuals and it measures the responses. That's the main idea behind an experiment. I mean, the goal of an experiment is to understand cause and effect. That is the goal of an experiment for it. We want to determine whether a treatment causes a change in response. Does spending 2 hours on a computer increase somebody's blood pressure? That was what the picture was before on it. So to see a response to a change, we have to impose a change. So to see a response to a change, we have to impose a change. We have to deliberately do something to it. And that's what this says. In order to measure a response, we have to impose a change on it. And it's really important you distinguish between observational studies and experiments. Observing, there is nothing done to the person. You're just observing. There is no change imposed on them. There's no treatment imposed on them. An experiment, you're causing a change and you're measuring the response. When you're reading a prompt, that's a really important thing to do. So when you're dealing with these, observational studies of the effect of one variable on another could often fail because there's confounding variables between them. A lurking variable is a variable that is not among the explanatory or response variables in a study that may influence the response variable. And what happens when we go through that, confounding occurs when two variables are associated in such a way that their effects on response cannot be distinguished from each other. So I tried in the beginning with this. The one you really want to focus on is confounding. But that's where this picture came into play, and why I wanted to go over this is we can't tell if lack of activity from an observational study is what's really causing the blood pressure to be high or the computer time to be high. I mean, it could be that. That's a confounding variable. They just may not be active people, and that's why they spend a lot of time in front of the computer, or that's why their blood pressure is high, is because they're not active. So there's a confounding variable there. So by doing an experiment, I'm going to try and control that confounding variable. That's what that definition kind of goes through. So I wanted to kind of show that to help out with this definition of confounding. Is behind the scenes, there's some other variable that may be influencing the results, and we have to make sure we control for that. So well-designed experiments take steps to avoid confounding, and that's where our principles of experimental design come into play. And so that's why we really want to make sure we do that. Now, another example of confounding, if you think about it, just something with popcorn. You have 3 brands of popcorn: popcorn 1, popcorn 2, popcorn 3. You also have 3 different types of microwaves: microwave 1, microwave 2, microwave 3. And you want to know which is the best popping of popcorn, which one doesn't leave those hard kernels at the bottom of the bag after they pop in the microwave. So you put them in. You put popcorn 1 in microwave 1. You put popcorn 2 in microwave 2. You put popcorn 3 in microwave 3. And you pop them. Well, then you analyze the results. So what do you see? Well, you may see, man, popcorn 1 was great. But the problem is there are 3 different microwaves. So if I keep putting popcorn 1 in microwave 1, and I run the experiment again with popcorn 2 in microwave 2 and popcorn 3, and I keep doing it over and over and over, the question is it the brand of popcorn or is it the brand of microwave? And that's a confounding variable. I can't tell which one it is. I can't tell if it's the microwave I purchased or if it's the popcorn I purchased. And so that's a confounding variable right there, is I can't tell which popcorn's better because I don't know if it's the popcorn, I don't know if it's the microwave. So what we can do is we can do method B. And what method B does is it randomly assigns a popcorn to microwave 1, it randomly assigns a popcorn to microwave 2, it randomly assigns a popcorn to microwave 3, and it pops. And we look at which one's good. And then we do it again. We randomly assign again, we randomly assign again, we randomly assign again, and we pop. And we see which one goes. And we keep doing this over and over and over. And by doing that, we are trying to control for that confounding variable, and by doing it, we're replicating the experiment a lot. So that's what a confounding variable is. And here, I can't tell whether it's the microwave or the popcorn. But here, by randomly assigning the popcorns to the microwaves, I'm controlling for that confounding variable. Now that we have this down, let's look at the language of experiments. And so the language of experiments, an experiment is a statistical study in which we actually do something. We impose a treatment on a group of people or animals or objects. We're looking for a cause and effect, so we implement We impose a change on something, we want to measure it. Well, the change is the treatment. What we are imposing is the treatment. The people, the animals, the objects that we're imposing the treatment upon are the experimental units. And what we're trying to measure is the response for it. So the basic vocabulary we have is treatment, experimental units, and subjects. That's the basic vocab. And so a specific condition applied to the individuals in the experiment is called a treatment. And so you have an explanatory variables. A treatment is a combination of specific values of these variables. Now, experimental units are the smallest collection of individuals to which the treatments are applied. Those are the people, animals, or objects, but when they're people, we call them subjects. Some of the other definitions of vocabulary for the language of experiments. The explanatory variable in an experiment is often called factors. They are referred to as factors on it. Now, many experiments study the joint effects of several factors, so several explanatory variables. In such an experiment, each treatment is formed by combining a specific value or a level of each of these factors. And so this part, I'd say, is the non-basic vocabulary. And so we want to find a way to make it a little bit easier to understand. So I have explanatory variables, which we call factors, and then sometimes there's different levels in those factors for it. And I want to look at a response that I want to measure based off a treatment. So let's look at this. Factors and levels. So let's say I have tons and tons and tons of ingredients. And what I'm going to do is I'm going to grab some ingredients and equipment in the kitchen. And of those ingredients and equipment in the kitchen, I'm going to use an oven, I'm going to use sugar, I'm going to use a flour, and I'm going to use eggs. Those are my factors. Those are my variables. So I go in the kitchen, I got an oven, I got sugar, I have flour, I have eggs, perfect. Those are my explanatory variables, those are my factors. Now when I use an oven, there's different settings. There's different levels, there's different temperatures you can set it to. When I do sugar, I can use a tablespoon. By the way, I can even use a measuring scale on it as well for more accurate cooking. Or same thing with flour. I can use different cup sizes, or I can use a measuring scale on it. There's different settings for those. And for eggs, does it take 2 eggs? Does it take 3 eggs, 4 eggs for the recipe? Who knows? And so those are different levels inside the factors. And then when we combine all that together, we mix the eggs with the flour, we mix it with the sugar, and we cook it for a certain temperature. Lo and behold, we made a cake. Amazing. And so when we eat a cake, how does it taste? Is it too dry? What's the color like? What's the consistency like? And that's what you're measuring. That's your responses for those characteristics of the cake. That's the response that you're measuring on it. Those are the outcomes you're looking for. And so that's really the main idea behind factors and levels. So hopefully this idea of what a factor is versus what a level, factors should be easy. It's your explanatory variable, but what are the levels? Well, think in context. If I have an oven, there's different temperatures. For sugar, I can use a different amount of measuring cups on it. Same thing for flour. For eggs, I can use a different number of eggs. And so that's where the levels come in. Now that we have that language down, let's look at how we design experiments. And we do want to keep some things in mind. First, I know this is not on yours, but that's because we want the first thing you see to be a good experimental design. Now, this is a good experimental design. And we'll go over the principles a little bit later, but this is a good one. You have your experimental units, you're doing random assignment, you have different groups they're going to, you're imposing a treatment on the groups, and you're comparing the results, the responses on it. That's a good randomized comparative experiment. Like I said, that's not the next slide in your notes, but we wanted the first one for you to see to be a good one. Well, now it's the bad one on it. Now, how to experiment badly. So let's say, for example, a high school is offering a review course online to help prepare them for the SAT. And so what happens is they're taking a group of students, they're putting them in an online class for the SAT, they are going over test-taking strategies, they're going over practice problems, practice tests, they're drilling them into them, and then they go and they take the SAT, and my goodness, look at their scores. Well, what are we comparing their scores to? If you look at that, what we did was we took a group of students, we gave them a treatment, all of them, and we just looked at their SAT scores. But we're not comparing them to anything. We take a group of people, we do something to them, and then something happens. Well, of course that happens. You have a group of people, you prepare them for the SAT, and oh, look at that, they have SAT scores. Now, how are they? Well, how are they to who? What are you comparing them to? We can't tell if there's an improvement or not from this SAT prep class. That's a bad experiment. I mean, most experiments go that way on the case. So they go like, they go like, here's this group of people, you impose a change, and look at that, a change occurred. Magic! You imposed the change. You prepped for them for the SAT. So of course their scores are going to go high. So the experiment badly, that's what really happens, is you have an experimental unit, you give a treatment, and you measure the response from it. There's no comparison. There's no real cause and effect on it. Did that treatment cause it? And what change occurred? What was the control? What are you comparing it to on it? Now, in a lab environment, simple designs do work well. But for experiments with animals or people, we deal with many variables on it. So outside the lab, badly designed experiments often yields worthless results because of confounding variables. You hear we're saying that a lot, and so we have to control for those confounding variables. You hear me saying that a lot as well in this video for it. So when we want to do a good design, we want to use a randomized comparative experiment. And what that means for a randomized comparative experiment is that you are going to take it and you're going to do a random assignment for the experimental units into the treatment groups. You're going to do it random, and the way you're going to do it random assignment is the same way we learned in 4.1. You can do identical slips of paper and a hat, mix thoroughly without peeking, draw, don't replace, draw again. I mean, the stuff we did for that in 4.1 is how we're going to do random assignment in this one. And what it does is the experimental units are assigned to the treatments at random, and by doing that, we're using a chance process, and that chance process allows us to control for those confounding variables that may be behind the scenes. So comparison alone is not enough if the treatments are given to groups that differ greatly. I mean, bias is going to result. So by doing random assignment, we're controlling a lot for that confounding variables for it. So some of the techniques for randomization, we used table D. We use identical slips of paper and a hat. You use random integer on your calculator for it as well. And those are some of the ways we did randomization. You're in 4.1, you're going to do it the same way here. And so we go here. Here's the comparative randomized experiment for it. A completely randomized design. The treatments are assigned to the experimental units by chance. And that's right here. They are occurring by chance. You are doing some random assignment. You're putting identical slips of paper and hat. You're doing a table D. You're doing a random integer on your calculator. And that is how you are separating the groups and imposing the treatments on them. That's a completely randomized design. And what may happen is you may need to include a control group. And that control group receives an inactive treatment or an existing baseline treatment. And so when you're looking at a control group, you may ask yourself, well, how do I know? Do I need a control group? Well, yes. If you want to determine if one treatment is better than the original on it. So if you want to determine if treatments, a new treatment or any treatment is better than the original. So if there's an original treatment and you have, oh, we got a new medicine on it, we want to know if it's better than the original. Well, then you're going to need a control group as well. You're going to need the new treatment, you're going to need the original, and you're going to need a control for it. That way you can compare to it. Sometimes that control group might be a placebo, and we're going to go into that as well. Well, when do I not need a control group? That's if we want to compare the effects of several treatments to each other. So which works best? Treatment A, treatment B, treatment C. Well, I want to compare them with each other. So then I'm not going to need a control group for that, because I want to know which one is better of those three. Which one gives the best responses, either A, B, or C. So no control groups needed for that one. It's when I want to determine if it's better than the original. Then I'm going to need a control group for it. And this is really what a completely randomized design looks like. Throughout this video, you've heard me say the word confounding. You've heard me, control for confounding variables. We've said random assignment a lot. And I've said the word replicate quite a few times. There's a reason why. Those three things are the three principles of experimental design. And I wanted to say them over and over during the lesson when they mattered. And so you can kind of hear the idea behind them. This is only one slide, but it's a really, really important slide. It is the principles behind all of it. Control, random assignment, and replication. Those are the three principles of experimental design. You are expected to know what they are and their purpose. So you're expected to be able to state what they are, and you are expected to tell me their purpose. It's kind of like a two-part problem on it. So make sure you, when you're listening to this, you pay attention and not just know the words, but what are their purposes in the experimental design. First, control. For lurking variables that might affect the response. I'm going to use the word confounding here. And so you heard me say that quite a few times in here, is we need a control for those confounding variables behind the scenes. Well, how do we do that? Well, one, we use a comparative design. We use a comparative design right there. That's going to allow us to control. Well, how does that allow us to control? Well, we ensure that the only systematic differences between the groups is the treatment that is being administered. So look right here. That's the treatment that's being administered. It's the only difference between those groups. So we're going to go into this a little bit more. I want to show you this example first on it. Next is, well, let's continue with control. What does control do? What's the purpose? Well, it ensures that influences other than the experimental treatments operate equally on all the groups. It's controlling for those confounding variables. Any other influences that may be going on, they are being equally distributed across the groups. They're having an equal impact on all the groups. It's not just impacting one group over the other. Again, we're going to go through this a little bit more a little bit later. What about random assignment? We're going to use chance, impersonal chance. We're going to assign the experimental treatments. This is going to allow us to create roughly equivalent groups of experimental units by balancing those effects of lurking variables or confounding variables that aren't controlled in the treatment. It creates groups of experimental units that should be similar in all respects before you apply the treatments. So when you create your groups, that random assignment right there, it's creating group 1 and group 2 to be roughly similar before we apply those treatments. That's going to help us balance the effects of any confounding variables behind the scenes. And then the third idea is replication. We want to use enough experimental units in each group so that any differences that we measure in the effects of the treatment can be distinguished from chance. It didn't just happen because of chance, it happened because of the treatment. We use enough subjects so that when we measure the response, we can make a statement saying that this effect happened because of this cause. We can look at the response and say that treatment did this and that treatment did this. And so if you look at this design, what does replication allow us to do is we can see with these results, we use enough people in treatment 1 and treatment 2 and group 1 and group 2, and we use enough people in the experiment. So enough people were chosen in the beginning that when we split them in groups, the groups had enough subjects in them that received the treatment that when we see the results can be distinguished from chance outcome. It happened because of the treatment. That's replication. A completely randomized design for experiments, it illustrates these three principles. So on your notes, I believe on your notes next, you should have a blank slide. I have a graph paper here for it. And we're going to kind of go through quickly this. So let's put this into an example. I want to take all the AP Statistics students. That's my that's what I'm going to do the experiment on. And what happens is, let's just say, to make it easier, there are 120 of you. And so that's going to be the experimental units. What I'm going to do is I am going to randomly assign them to two groups. So I'm going to have two groups on it, and I'm going to mark it this way. I'm going to randomly assign. Well, Mr. Rainswork, how are you going to randomly assign? That's a wonderful question. You know what I'm going to do? I'm going to put the names of all 120 students, all of you, write them down on identical slips of paper, and I'm going to place them in a hat. I'm going to mix thoroughly. And without peeking, I'm going to draw out 60 names. The first 60 names are going to go into group 1. And what group 1, you first 60 students, you are going to be assigned only the quiz BC problems. And there are going to be 60 of you. The remaining 60 names in the hat, you're going to group 2. And you're going to be assigned book problems for homework. And I'm going to take your performance on this Chapter 4 test, and I'm going to look at both groups, and I'm going to compare the performance on the Chapter 4 test. Now, when you are doing a problem like this, look at this at the end of the video, is you should also have writing down here that goes into more detail for it. A picture is not enough. A diagram is not enough. I'm just showing you this to kind of talk about our 3 principles of experimental design, because I don't know if you're aware, we addressed them in this diagram. Well, you want proof? So let's do this. Control. That's the first principle of experimental design. Well, remember, control says we want to control for any confounding variables that might affect the responses. And we do that by using a comparative design. And look at this. Am I doing a comparative design here? I have a group 1 to group 2, and I'm comparing something after I impose a change. So I've got that set. Let's see. I want to ensure that the only systematic differences between the groups is the treatment being imposed on them. So did I make sure that happened? So here are my groups. Here's treatment 1. Here's treatment 2. So I did manage to control for any confounding variables on it, because the only systematic difference between those two groups, group 1 and group 2, is the treatment that is being imposed on them. There is your control. The next part is random assignment. So control tries to control the impacts of confounding variables other than the factors being tested. The only difference is the factors being tested. You want conditions to be similar in all the treatment groups. You're trying to control those conditions. Now, what random assignment does, well, let's look at our definition. Random assignment tries to use impersonal chance to assign the experimental units to the treatments. Well, did I do that? Well, yeah, right here. I used chance, random assignments. I put all your names in a hat. I mixed thoroughly, and I did not peek. And I drew out the first 60, and they went into group 1. The remaining went into group 2. I used chance to assign each of you to those groups. And what did that do? Well, that helped balance the effects of any confounding variables on it. Maybe a student who doesn't do well ends up here, but you know what? By chance, it could have happened here too. It wasn't that I put all students who don't do well in one group. I randomly assigned them. It controlled for this. Any confounding variables, I tried to balance the effects between the two groups by using randomization. What's the third one? Well, the third principle we have is replication. Did I not use enough subjects in the experimental units and in the treatment groups for it? so that when I make my comparison, I can make my statement that this treatment caused this effect. Doing the book problems was better than doing the quiz BC, or vice versa. Did I use enough subjects to make that comparative statement? That's replication. So look at this. Did I use enough subjects here? Didn't I use enough subjects in my group so that when the outcome happens, any differences between the two groups can be distinguished by chance? I can say, you know what, whatever results I get are because of treatment 1 or because of treatment 2. That's replication. Used enough subjects so the results can be put to the treatments and not just the chance. It's because of the treatments on it. So that's a completely, that's the principles of experimental design. I want you to realize we do cover it on it, but you do need to know what they are and what their purpose is. So even, I know these are on your notes and you're just filling in a couple of words, but rewrite them. Label it on the picture like this and kind of, here, kind of state what is control in this area, what is random assignment, what is replication, what does it mean? I mean, control, we talk about, is it allows us to ensure that the effective response, I have a comparative design, and the only difference between the two groups are my treatments. That's the only difference between the two groups. And that allows me to do it. So I control how my groups are assigned, what treatments they're getting, so I can make a comparative result. Random assignment. Well, I make sure I do random assignment because it balances the effects of any confounding variables that may be behind the scenes for it. And I do replication so that way I have enough subjects so that when the treatment's there and I get my results, I know it's not because of chance, but because of the treatments. So still always go back to this. It's one slide, but it's a really, really, really important slide. So the last but not least, if you stuck around for 32 minutes on this, is this check your understanding. I'm going to let you pause it and kind of go through this. So hopefully you read it, and here's where we are. We have 29 students, and we're randomly assigning 15 to the first treatment, which is a video practice performance, and ask the students to evaluate it and then discuss the video with a small group of other students. And we have 14 remaining students that are a control group who watch and evaluate the videos all by themselves. And at the end of the semester, the discussion group students evaluate their final performance more accurately, is what we see. So number 1 asks us to outline a completely randomized design for this experiment. You might want to take out a separate piece of paper for this. I know there was not a lot of room on the notes, but this does involve a diagram. And so when we do this, we have, in this case, our 29 students. We're splitting them into 2 groups. I bet you we should use randomization for that. 15 here, 14 here. We're going to specify what's the treatment for the 15, what's the treatment for the 14. What are we imposing on those groups? And then it did say they compared at the end. Which group did better for it? So basically, here's your first diagram. And you have to draw the diagram. I have 29 students. I have random assignment for them. And we will have to describe always in words, not just with a diagram. Saying random assignment is not enough. You're going to have to describe it. And then you have group 1. Well, right now, the problem with this outline is don't just copy this down exactly because this isn't detailed enough yet. Well, what was the first treatment in here? Well, the first treatment was small group. They analyzed their video in small group, and we'll be specific in our description. That's the other reason why you have to write a sentence is anything you don't draw on the diagram, you can save yourself in the sentence. What was group 2? Well, group 2 was the doing it all by themselves, a lone group. How many in each group? That's a good question. Well, there was 15 in group 1, there was 14 in group 2. So 15 students got the first treatment, 14 students got the second treatment. And what they do afterwards? Well, another good question. They compared the evaluations at the end. That's a completely randomized design. That's a diagram. We're still going to describe. And what happens is the describings can take up a lot more. We're going to try and save anything we didn't quite address in the diagram. We're going to try and save in the writing. So when we're asked to describe how you would carry out the randomization, so we're now asked to describe how we would do this, which is a really good thing because that we already know how to do from 4.1. And I've already described that in this. I'm going for the hat. There's 2 ways. You can put the names of all the students on equally sized papers into a hat mix thoroughly, no peeking. The first 15 selected, without replacement, they're going to go into group 1, which is the small group evaluation. The remaining 14 are going into group 2 for self-evaluation. Now, I have yet to I should still make a statement, and this isn't number 2, but I would still, if I'm writing, I would say, well, what are we going to do at the end? We are going to compare the evaluations of both groups. I'm still going to say that in words on it. So that's the description. Now, method 2, if you want to be that student who uses table D, good for you. Way to be a traditionalist. Using an alphabetical list of the students, assign each student a number between 0, 1, and 2, 9. Pick a line of the random number table, let's just say 137, and read off 2-digit numbers until you have 15 numbers between 0, 1, and 2, 9, ignoring number 00, 30-299. These students belong in the first treatment group, which is going to be the small group evaluation. The rest of the students are going to go into the other group where they watch the video alone. A lot harder to say than put the names of the students in the hat, mix thoroughly, no peeking, draw out one at a time without replacement. The first 15 go to group 1, the ones that remain in the hat go to group 2. Done. I prefer method 1 on it. So what does number 3 say? Number 3 says, what is the purpose of the control group? What's the purpose? Why do we have a control group? Well, it's to have a group with which to compare the treatment. We want to know, is small group evaluation better than doing it by themselves? So we're trying to compare is one, how does it compare to the other? So we're going to need a control group for this. Presumably the students have been evaluating their own performances by themselves. If you incorporate such a group in your experiment, you can evaluate whether the group work is actually better. The purpose of a comparative group is to ensure that the only systematic difference between the groups is the treatment administered, which in this case is the group work. We want to make sure that is the only difference between those groups. So you can rewind this video, go through this part again on it. Notice the principles of experimental design are one slide, but really still important. But Mr. Nichols should be finishing the rest of the 4.2 video on it.